Okay, so just a little quick review. We were looking at the mean value theorem, which basically says that the derivative evaluated at a point is equal to f of b minus f of a over b minus a. And so what we were doing a lot of was solving for c to figure out what that point was that would make the mean value theorem true. If we couldn't use the mean value theorem, meaning there was like a corner or cusp or a vertical tangent, then we would put that. Let's see, we did that one. And then we looked at these problems that are ones that basically say that at some point during like a time interval, like either a temperature has to be at least something. There's ones like about runners that at some point they have to be running at least this many miles per hour. Things like that. Just using the mean value theorem, which isn't really a whole lot other than just like setting it up to prove that that has to be occurring. So the next step says to use analytical methods to find the local extrema and then find the intervals on which the function is increasing and decreasing. So 16, g of x is equal to x squared minus x minus 12. And so essentially what I'm doing is I'm using the second derivative test, and I'm going to find if I have any mins and maxes like we were doing in the first chapter or first section. So first derivative of this would be 2x minus 1. Second derivative would just be 2. We'll talk about that in a second. Anyways. All right, so set this equal to 0 and solve. So then we would end up with that x is equal to 1/2, which is my critical point. Now, this over here, there's nowhere to plug this in. We haven't had one like that happen. So essentially, this is telling me, though, that this has to be a min because it's greater than 0. I don't have to even plug it in to know that it's going to be a min. So we have a min at x equals 1/2. So then I need to find where that point actually is because I'm finding the point and then I'm going to be finding the interval where it's increasing and decreasing. So to do that, we plug that into the original. So g of 1/2 is 1/2 squared minus 1/2 minus 12. So 1/4 minus, I'm going to go ahead and put this, get common denominators here, so over 4. So minus 2 over 4, and then minus 48 over 4. So that gives me a negative 49 over 4. A lot of times we just leave it that way. If you want to convert it into, a decimal, you can. So the answer to part A, we have a min at 1/2 and negative 49 over 4. So that's our point. And then we're looking at, for increasing and decreasing, we're just looking at, okay, well, what's happening to this function? And this original function is just a parabola opening upward because it's positive. And so basically I know that it's decreasing until I get to my vertex, and then I'm increasing. And so the min value is where that's happening. So the increasing are intervals, though, and so let's see, B is increasing and C is decreasing. So if I have a min, that means everything before that had to be a decreasing value, and then everything after that has to be an increasing value. So decreasing would be from negative infinity to 1/2, and we do include on that because it's technically decreasing all the way up to that point, and then it's turning around. And then we're increasing from 1/2, including to positive infinity.
It gives us increasing and decreasing.
It's asking us for increasing and decreasing, okay. So technically we're finding this.
Right.
But you're really just looking at, one, this is a parabola, so I know what it looks like. But essentially when you have a min and a max, it's just like if you have like your first min, obviously you had to be decreasing up to that point. And then if you're going past a min, anything to the right of that has to be increasing if it's a minimum. And then same thing for like a maximum of like, okay, well if I have a maximum, then I was obviously increasing on the left and then I'm decreasing on the right. So you don't really have to like mathematically like do anything with these ones other than just say where that's happening. And obviously if they have multiple maxes and mins, then we're going to have multiple intervals of increasing and decreasing as well. So if we look at 22, y equals x to the fourth minus 10x squared plus 9. Then I've got first derivative is 4x cubed minus 20x. Second derivative is 12x squared minus 20. So then we set our first derivative equal to 0. I'm going to need to factor this, so I would take out a 4x. And then that leaves me with x squared minus 5. Yeah. So basically I have that x is equal to 0, or I have that x squared is equal to 5, meaning that x would either be positive square root of 5 or x is negative square root of 5. And so I have basically 3 different points that are either going to be maxes or mins that we're going to plug into the second derivative. So I'm just going to do this y double prime of 0. So if I plug in 0, I get negative 20, which is less than 0, so that is a max. At negative square root of 5, then I've got basically just 12 times 5, so 60 minus 20, so that's 40, which is greater than 0, so that's a min. And then same thing's going to happen with positive square root of 5. We're going to end up with, because that's 60 minus 20, so again that's 40. So that's another min there as far as like that goes. And so then I have to plug each of these numbers into the original to figure out what what's the word I'm looking for? What the like points are for the maxes and mins for part A, and then we'll find the intervals of increasing and decreasing between those intervals or between those points after that. So let's see, y of 0 would just be 9. So that's, I'm going to go ahead and set this up down here. Max, min. All right, so at 0, 9, I have a max. And then negative square root of 5. Raised to the fourth, that's just going to be 25 minus square, that's 5 times 10, so minus 50, and then plus 9, so 25 minus 9, 16, negative 16. So then there's a min at negative square root of 5 and negative 16. And then same thing is going to happen with the positive one, because obviously if it's being squared, the signs are staying the same. Like nothing changed with that. So y of positive square root of 5 is going to also be negative 16 then. So at square root of 5 and negative 16, then I also have a min. So in like order logistically, the max goes between the two of them. because we have negative square root of 5, 0, and then square root of 5, like, going across left to right. So that means up to this point, and our intervals of increasing and decreasing are always going to have closed brackets unless it's at infinity. So, let's see, I'm going to go ahead and set up increasing and decreasing so I can just go left to right and write them down as I go. All right, so if the first thing I have is a min, then that means I had to be decreasing first. So I was decreasing from negative infinity to negative square root of 5. And then I went from a min to a max, so that means I was increasing then from negative square root of 5 to 0. So both of those ends are going to be included. Then going from the max to the min, I'm decreasing from 0 to positive square root of 5. Again, both of those are included. And then after the last min, I would have to be increasing again. And so we would be increasing then from square root of 5 included to infinity, obviously not included. So, does that kind of make sense?
Yeah.
Fortunately, it's not really a whole lot more than what we did in the previous section. It's just the increasing and decreasing part. And so, sometimes I'll kind of draw out what I think it looks like so that I can see it just to make sure, but usually not too bad. All right, then the last stuff in this section is finding all possible functions with the given derivative. So what this means is I'm finding the antiderivative, which is going to lead us into integrals and stuff like that in chapter 6 later on. So we're working backwards. So instead of us taking the derivative and taking what the exponent is and putting it out front, now I'm essentially taking what was out front and putting it up to the top. Essentially, I'm adding 1 to my exponent. So I'm working the other way. Instead of subtracting 1, I'm adding 1 and then figuring out what number goes in front. These ones are going to be pretty base level, easy ones. Obviously, they're going to get harder, but they're starting you out with, how when we started with derivatives, it was what's the derivative of 2x? It was very simple. They're starting you out that way with antiderivatives, essentially. So, 30, we have f prime of x is 2, or is equal to 2. So that means the derivative. So I'm saying, okay, well, what original function gave me that? So if this is a constant number, then obviously there could have only just been an x there as far as, it wasn't raised to anything. So f of x is equal to 2x. But what happens when I take the derivative of a constant number? Ignore what's written right here, right now. If I just said, tell me the derivative of 3, what would you tell me it's equal to? 0. So that's just gone. So I need to account for the possibility that there was something else here with this original function. To do that, we add c. And it just says, here's the constant. Eventually, when we get into integrals, they'll tell us, potentially what the original value was, or we'll have a way that we can find it, and we'll be figuring out, okay, what was the original constant value that was there. But right now, we don't know what it is, so we just add that plus c to kind of be a placeholder of, hey, it could just be 0, there may not have been anything, but it also could have been 2x plus 7. And that the plus c accounts for negative numbers as well. But anyways, so yeah, that's the biggest thing people forget when they do this section is the plus c part. So I try to emphasize that a lot. 32. F prime of x is equal to the sine of x. So the other way that I like to think about these when it's not just something like 2 or, 5x or whatever, is I like to say, okay, what function has a derivative that would be equal to the sine of x? So which function? Do you remember which derivative? Which essentially it's got to be, obviously it's got to be trig function. Which trig function is the derivative sine of x?
Be negative cosine.
Yeah, so that's good because I was getting ready to point that out. And so sometimes you have to watch the signs because even though we're not having to add an x or whatever. We're just changing the function. The derivative of cosine is minus sine. So if this is positive sine, we got to put that negative on there. But obviously, you already knew that. So minus the cosine of x and then plus c, because we still have to account for that as well on the trig ones. 34. F prime of x is equal to 1 over x minus 1, and they tell us that x is greater than 1. You don't have to do anything with this. This stipulation is on here because the original function, with what the original function is, this has to be a stipulation or this doesn't work, because we would have something that's undefined. So this one may not be as obvious. Do you know what? Let me ask it this way. What would have the derivative of 1 over x?
The ln.
Yep. So since this is x minus 1, this is what goes inside.
Oh, okay.
So this would be the ln of x minus 1. And then plus c. So this x being greater than 1, obviously it's going to cause a problem down here at the moment, because if it's equal to 1, I have 0 on the bottom. But that's not really the ultimate problem. The ultimate problem is here, because I can't have 0 or a negative in a log. So that's why they've given me this. But as far as the actual antiderivative, I ignore that. If they gave us something like, I don't have a lot of examples here. Let's see. F prime of x is equal to 2x plus 1, and then minus the cosine of x. And they wanted us to do this one, just so we can see something that's a little bit more challenging. We take the number that's in front. Well, let me back up. I always look and say, okay, I need to take the variable and raise it to the, add 1 to the exponent. So that would mean that this has to be squared. So I'm like, well, what happened to put this here? Well, that was essentially they just multiplied. They just brought the 2 down in front to get to here. Because sometimes if this is like a fraction or something, which, like I said, we'll get into that eventually. All these ones are pretty simple. Then you have to be like if this was 2/3, then I'd have to be like, okay, well, there's a 1/3 in front of here, because I'm trying to figure out, okay, what number was in there. So you probably will end up enjoying that as well, because it's kind of a puzzle of oh, what did they do to get to this point? Anyway, so that would be that part. Over here, we just have a 1. Obviously, that means that has to have had an x with it, so plus x. And then minus the cosine of x. So what has a derivative of minus cosine?
Negative sine.
Yep, because the derivative of sine is cosine. Yeah, because the derivative of cosine is minus sine. I always have to think about it. And then on this one, again, we would still add our plus c at the end. And that's, like I said, it's leading us into integrals. If we have indefinite integrals, those will also have a plus c on them. When we have a definite integral, meaning they've told us, we're from this value to this value, we don't have that technically. Okay. But that's, way down the road. But anyways, it's good to just, get used to, the plus c now, because then you'll remember it when you get farther down the road. But anyways, that's all in this section. Are there any questions about any of this stuff? No, I'm trying to remember. Did I give you problems the other day?
No.
Okay. So 1, 3, 11, 15, 19, 29, 31, and 33. So these last 3 are just the antiderivatives that we just did, so those should be pretty quick. And then 11 is just a variation of the temperature problem that we did, essentially.
You said you tested on chapter 5 before Christmas?
No.
Oh.
No.
I was about to say, how in the world did you guys?
At most, I get through 5.1 usually.
Okay.
Yeah, no.